So, welcome everyone to Guided Study Group Week 12 of Statistic 100. And so, as you guys know, today is the last day of the materials, and also the next week, no, actually Sunday is going to be the final exam review, and so we're gonna be working on the two last lesson today. It's lesson 11 and lesson 12. Which is also the main part of statistics, where we talk about hypothesis testing and some of the precautions that you need to be aware of when we design any statistical model and experiment. So the first one is lesson 11, hypothesis testing. So a significance test is the one defined as the one that examines whether the known hypothesis provides a plausible explanation of the data. So when we do a significance test, what we need always at the first step is to identify what is the known and alternative hypothesis. So the known hypothesis is a statement about a parameter or one of the population's value where and then it does not involve the data. So whatever stated in the known hypothesis is kind of like maybe the population means or population proportions and will never be the sample statistic. Then the alternative hypothesis is a statement about a researcher hypothesis or question of interest. And again, it's about a parameter, but it's going to be different from a known hypothesis. It can be something as easy as known hypothesis is where you have the mean equal to 0, or an alternative hypothesis can be mu different from 0, bigger than 0, or smaller than 0. And then after we identify, so first of all, we need the question of interest, and then the known and alternative hypothesis. Then we have to identify what test statistic that we're going to take from the sample of data. And then we're going to start to compare that with the value in the known hypothesis, and then make our conclusion based on the p-value and the threshold of alpha level. So the test statistic is defined as a measure of the difference between the data and what is expected when the known hypothesis is true. So again, that is one of the indicators to see if a sample shows us if the population is matching our expectation or not. And test statistic, again, as a summary of the data, but this allows us to make inference about the populations. The test statistic is typically standardized so that a p-value can be obtained from a reference distribution. And so if you proceed to statistic 200, you're going to see the fact that your p-value is going to be calculated differently, and now it's usually due based on statistical software. But then each of the p-value and test statistic of our sample is going to depend on the distribution that we assume our population follows. It can be a normal distribution, t distribution, f distribution, or some other things. To construct and conduct a hypothesis, as I briefly mentioned, we need the known and alternative hypothesis. But before that, you should be able to identify what is the question of interest and what are you trying to determine based on this experiment. Then collect and summarize the data so that a test statistic can be calculated. Use the test statistic to find the p-value. So here the definition of the p-value is the likelihood of getting our test statistic more extreme if the known hypothesis is true. And interpret what the p-value says and make the decision. So usually we're going to have a threshold of 0.01 and 0.05, where when you proceed to statistic 200, we're going to call these alpha level. And if you learn to higher level of statistic, we're going to learn things about like power level and confidence level. When you have p-values smaller than these threshold, like smaller than 0.001 or smaller than 0.05, then this one is going to be called the result is going to be highly significant. And in the denominator, when it's smaller than 0.05, it's only significant. And when it's bigger than 0.05, usually we say that it doesn't really have no significance, and we cannot reject the known hypothesis. We do not reject the null hypothesis, but it doesn't mean that the null hypothesis is true. It can only, we can only conclude that we don't have enough evidence to reject the null hypothesis. Then we also have lesson 12, where we learn about some of the precautions that we need to care about, significance testing, and also the ethics of experiment. So some of the things that we need to care about is the large sample rule, small sample rule, and multiple testing. So when you have a really, really large sample, then you can detect the smallest of departures from the known hypothesis. So any deviations from the values in the known hypothesis can be detected with a larger and larger sample. And then in those studies, ask yourself if the magnitude of the observed difference from a known hypothesis is of any practical importance. So from the what we're basically saying here is that with a large sample, you can detect even the smallest difference from what is expected in the known hypothesis. And sometimes you have to ask yourself if that difference is of practical importance, and if it's not, we don't need to try with a larger and larger sample. Then the second rule is a small sample. It's saying for very small sample sizes, a very large departure of the sample results from a known hypothesis may not be statistically significant because of maybe the sample is biased or it's too small to make any practical conclusion. This should motivate one to do a better study with a larger sample size. And then the last rule is the multiple testing rule. When you have a large number of significant tests that are conducted, some of the individual tests may be deemed significant just by the chance, even if the known hypothesis is true. So, which means that the more tests that you actually conducted, since you always have a certain chance that you're gonna make, like in every test, there's always a certain chance that you're gonna conclude that your test result is significant. The more tests you do, there'll be some chances that some test results are significant just because of that probability and not because of the actual nature of the test. And some ethical conditions when you do any statistical experiment design is that you have to be aware of the design and the treatment used in experiment, especially with medical study, where the use of painkillers or maybe things like when you learn about the role of ibuprofen, then in those cases, the treatment you're trying to apply for your patients have to be carefully designed because that can create harm or affect the benefits and privilege of your patients. Regardless if the studies is beneficial to the patients or to the subjects or they volunteer to do the study or not, we always need to make sure that they are informed of all of the consent and they have to sign the document and be aware of the information that they consent to. Avoid coercion. So try to maintain the voluntary nature of participation in the study. And always, as I briefly mentioned, avoid harm to your subjects of study. Now, with all of those things in mind, we're going to do the practice questions and problems. Again, feel free to mute me anytime in this practice questions sections if you want to work on it on your own. The first one, true or false, if the p-value is small, then the sample statistic is a poor estimate of the population parameter. So when you have a p-value is small, say in this case you have p smaller than alpha, it only means that your parameter is whatever your hypothesis is about, the result is significant, and it doesn't say anything about the population parameter or the sample statistic. It only say that maybe our estimate of the population parameter based on the sample statistic might be different, or it can be it might not match what we expected in the known hypothesis. And it doesn't have to be a poor estimate. Sometimes your p-value is small, but maybe it's not small enough to be smaller than the threshold. Then you cannot conclude that the sample statistic is a poor estimate of the population parameter. So in this case, the answer is 4 because they don't actually specify how small is the p-value. That's the first reason. And then the second one is that it does not necessarily mean that the sample statistic is a poor estimate of the population parameter. Sometimes they can be of a certain difference, but it is not of practical significance. So the difference is so small that you cannot conclude that it's a poor estimate of the population parameter. The second one, again, mute me if you want to work on it alone. If the null hypothesis is true, then what does it mean? It means that the significant test might not, you don't have enough evidence to reject the null hypothesis. So it doesn't say if the significant test is one-sided or two-sided. So A and C are wrong. Now let's look at B and D. A significant test will never reject the null. It only means the fact that we don't have enough evidence to reject the null hypothesis, and it also depends on your threshold. Your p-value might be bigger than 0.05 but smaller than 0.01 but bigger than 0.05 but bigger than 0.01. So it can still be rejected. And so the answer is going to be D. And again, it depends on what threshold that you're looking for your statistic test. The third one, a researcher believes that the average size of the pine cones that fall from trees in a particular sections of forest is over 5 inches long. So I would say the null hypothesis is the average height is equal to 5 and the alternative is more than 5. To test some null hypothesis versus that, take a random sample of 200 pine cones from the trees in this forest and find a test statistic of z equal negative 1.28. The p-value for this test would be about. Now, as we say, the p-value is the probability of your z bigger than 1.28. In this case, here when you have it's equal to the mean value, your z is going to be equal to 0. This is based on z is giving us the hint about the normal approximation that we did last week. So if you look at the normal table, when your z is negative, you're going to see the fact that the probability of the population smaller than negative 1.28 is 10%. And this part is going to be 90%. And so the answer is going to be 90% because you're looking at the probability bigger than negative 1.28. And so the answer is B. Now similarly for question 4, it's asking if we want to test the hypothesis that mu is equal to 0. And the alternative is mu is different from 0. We use a large sample size and calculate the standard score of the test statistic to be z equal to 1.28. So this is your normal approximation. This is where you have z equal to 0 and your population average is equal to the population mean. Here is 1.28. So we're looking for the probability. Look at it here. This is a two-sided test. So you have to look at the probability that your p-value is equal to the probability of your z bigger than 1.28 plus your probability of z smaller than negative 1.28, because this p here is equal to the probability of z, absolute value of z different from 1.28, bigger than 1.28. So they're two-sided of the normal populations that we have to look at, this part and this part. So if you look at the normal table again, this part is 10%, and this is negative 1.28, and this part is again 10%. So your total p-value is going to be 20%, which is the probability of your z bigger than 1.28. If you want to have more reference or review this part, please feel free to look at the example in the online notes. Now let's go to question 5. Again, mute me if you want to work on it on your own. Compared to a large sample size, a small sample size is more likely to lead to. So a small sample size is more likely to conclude that your test result is significant, because a small sample size is more likely to be biased, and it's usually have a very big departures from what we expected in the known hypothesis. So, but then we also have the precautions about the small sample size, is that even though that departure may seem very big and significant, it's usually the result that we have overall might not be of any importance, because we know the nature of a small sample size is usually biased, and the departures might just because that we only capture a small part of the population and not the overall characteristic of the population. And so in that case, our answer is B, a result that is not significant. Now let's go to question 6. If there's a lot of variability from subject to subject, then it means that your sample is small, because it means that we can have a lot of big departures from the population mean. So A, it will be easy to reject the null hypothesis with a small sample. May be true. It will be likely that we won't reject the null hypothesis with a small sample. C, it will be easy to prove the alternative with a small sample. Now, what we're saying here is that it might have a big departures from the null hypothesis, but it does not necessarily follow the alternative hypothesis. Say if you have a known hypothesis is mu equal to some value, but the alternative is mu bigger than that value. In that case, a small sample can make your mu way smaller than A, and it does not follow the alternative. And so C might be wrong. A, it will be easy to reject the null hypothesis with a small sample. Again, it comes back to the precautions about the small sample size. It's saying we can easily reject the null hypothesis, but that result might not be of any significance. And so the answer is going to be B. It will be easy that we don't reject the null hypothesis with a small sample. Again, I might have to check back with question 6, because that is a little bit confusing to me at first, but we're going to come back to that at the end of this section. Now, question 7. In which situations is a hypothesis test more likely to end with a significant result? So, we are saying with the small samples, it's usually easier, with the bigger samples, it's just usually easier to detect a difference in the sample statistic and population parameter. And so, with the bigger samples, it's easier to end with a significant result. So we're gonna choose the bigger sample. So A and C are wrong. Now let's look at the treatment. If the treatment is very effective, the significant result is even easier to detect, because the difference in the result between the two groups, the control groups and the alternative groups, are usually easier to detect. And so the answer is going to be B, where you have that difference in the effectiveness of the treatment be amplified. Now that is the end of our sections. As I mentioned, this Sunday we're gonna have the final exam review from at 9 p.m. and we're gonna go through maybe some of the practice problems in the practice exam. So if you have time, please do your own review first and try the practice exam problems. So then I can look at your how you guys perform on that practice exam and choose some of the challenging questions to solve in the final sessions. Other than that, I'll pause the meeting here for a moment and pull up the answer for question 6. So I just have a track back at question 6, and so the answer is that it will be likely that we don't reject a null hypothesis with a small sample. And that's because, as I mentioned, with the large sample rule, is that we usually need a bigger sample size to detect the smallest departures from what is expected in the null hypothesis. And even though if our result for a small sample size test is significant, it's not likely to be concluded that way because of the biased nature of the small sample size. And so if you have any further questions with this, please feel free to email me during the weekend or anytime, and then I'll try to get back to you guys as soon as possible. So have a great weekend. I'll see you on Sunday.